to my channel. Today, we are going to solve one of the most interesting dynamic programming problem called ones and zeros. It's a problem where we need to build the largest possible subset of binary string while keeping the total number of zeros and ones under certain limits. This is not just a simple counting problem, it's a 2D 0 by 1 knapsack problem, and it will help you master multi-dimensional dynamic programming. So let's dive deep into the logic, understand each line of the code, and finally conclude how and why this approach works perfectly. So we will just recap the problem. We are given a list of binary string strs, two integers m and n. We must find the maximum number of a string that can be chosen in such a way that the total number of 0s is less than or equal to m and the total number of 1s is less than or equal to n. Here is two problem is given. Okay, example 1 and example 2. Okay, also a constant value constant is given, that one is that, as we have already talked about that. Okay, so we will just follow the step by step solution here. Okay, with full explanation. So let's understand each line clearly. Here in the first line, class solution, and in the second line we have just defined max form self comma strs and comma m and n. So here it define our solution class and function find max form, where strs is our list of binary string, m is the maximum number of zeros we can use, and n is what, the maximum number of ones we can use. We want to return the maximum subset size possible. Okay, so here we have written dp is equal to what, 0 into n plus 1 for I in range m plus 1. This initialized a 2D dynamic programming table of size m plus 1, okay, into n plus 1 filled with zeros. dp I j what, here dp I j, here in the line 11 you have seen that dp I j, it means what, the maximum number of a string we can form using at most I0 and j ones. We use plus 1, we use plus 1 because we include the case where we use zeros and 0 ones. Okay, so for s in strs, we loop through each binary string in the list. Each string is like an item in knapsack which has cost in term of 0s and 1s. 0 is equal to what? Yes dot count 0, and 1 is equal to what? Yes dot count 1. So for every string we calculate how many zeros and 1s it contains. These values represent the cost of the including this string in our subset. For example, if s is equal to triples times 0 1, so 0 is equal to what? 3, and 1 is equal to what? 1. So if we decide to conclude this string, we will consume 3 zeros and 1 1 from our available budget. So here in line 9, for I in range, m is equal to m comma zeros minus 1 comma minus 1. For I j in the range, n comma 1s minus 1 and minus 1. This is a core of dynamic programming loop. We traverse the DP table backward from larger capacity m comma n to smaller zeros and ones. Why backward? Because if we update from top to bottom, means forward, we might reuse the same string more than once in a single iteration, which would make it an unbounded knapsack. Okay. So in backward traversal, it ensured each string is counted only once, making it a like a 0 by 1 knapsack. Here we have in the line dp ij is equal to max dp ij comma dp I minus zeros j minus 1s plus 1. This line is where we make a choice for each state I comma j. Option 1, dot include this string, keep dp I comma j as is. Option 2, include this string, look at the dp I minus zeros, j minus 1s, the state after spending its 0 and 1s, and add 1 because we included one more string. We take the maximum number of two choices. Okay, So we have just taken example of the transition. Suppose current string is equal to 10, 1 0. So 0 is equal to what? 1, and 1 is equal to what? 1. We are checking dp 5 3. Then dp 5 3. So the max is equal to dp 5 3. So dp 5 minus 1, 3 minus 1 plus 1. So dp is equal to 5 3. So max what? dp 5 3. So dp 4 2 plus 1. So if including 1 0 give a better count, we update it, return dp mn. Okay, finally after processing all string, dp mn contain our answer, the largest subset size possible using to the m0 and n1s. So dry run example what? Let's dry run the smaller example. Str is equal to 10, 0, 1. So m is equal to what? 1, and n is equal to 1. So start with dp and initialize to all 0. First string is 1 0. So 0 is equal to 1 and 1 is equal to 1. So updated dp is equal to what? 1. Second string is 0. So 0 is equal to 1 and 1 is equal to 0. So updated dp what? 1. So final answer will be 2 and subset will be 0 comma 1. So here in this question, time and space complexity will be what? So it's the expression value time that we iterate each string len strs, and for each we loop over all m into n step. 0 len strs into m into n, a space dp table of size m plus 1 into n plus 1, 0 m into n. This is efficient for the given constant m comma n is less than equal to 100, len strs less than equal to 600. So from this question we can create takeaways that this is a 2D 0y1 knapsack problem, not just one constant but two 0s and 1s. So the dp state, that is dynamic programming state, represent capacity in both resource zeros and ones. We update in reverse to ensure each string is used as most once. So the transition checks both including and excluding the string. So from this question we will on the conclusion part that the ones and zeros problem is a brilliant exercise to understand multi-dimensional dynamic programming. We started by understanding that each every string behave like an item in a knapsack consuming a certain number of zeros and ones. Then we built a 2D DP table to keep track of every possible capacity combination. By updating the table backward, we ensured that the number of strings were used, maintaining the 0y1 property. Finally, our solution efficiently returned the maximum subset size, demonstrating the power of dynamic programming in handling like complex constraints. So remember, whenever you see a problem involving two resources and maximization, think of it as a 2D knapsack. So here we have just solved the problem and we will just run this problem here. So it will run as a test result. We have passes all the test case. Okay, two cases have been passed, and here it will be run on the system. Okay, just wait, it will run. It is taking some time. Okay, so basically in this question we have just solved 0y1 knapsack problem. So if you don't have any idea about 0y1